Welcome to the Significant Figures video.
By the end of this video, you should be able to identify which digits in a measurement are significant and which digits are not, be able to round to a specified number of significant figures, and be able to round calculated answers properly. So what is a significant figure? Significant figures are all the digits that can be precisely known in a measurement, plus a last estimated digit. So if you recall from the previous video on measurement, if we're measuring, say, the temperature of an object using this thermometer here, we know that our temperature reading is going to begin with an 8, then it's going to be 80, 1, 2, 3, 4, 5, 6, 7. Those are known digits. We know those digits precisely. But we can also estimate a last digit, which I'm going to call 0.5. Here, our precisely known digits are 87, and our estimated digit is 5. All three digits are significant figures. So why do we need to be able to count significant figures? Counting significant figures is the first skill we'll learn in this video. Why is it so important? The short answer is a calculated answer cannot be more precise than the least precise measurement from which it was calculated. Imagine the following hypothetical situation. I measure the mass and volume of a sample and find the mass to be 1.00 grams and the volume to be 3.00 milliliters. Each of these measurements were taken to 2 decimal places. Beyond that second decimal place, I know nothing about the mass or the volume. If I want to calculate density from this data, which is a skill we'll be dealing with later in this unit, I can divide the mass by the volume. As you should know, this comes out to be 0.3 repeating. In other words, there are infinite 3's after that decimal point. Clearly, there's no way that we measured the density of this object to infinite precision. Therefore, if we reported the density as 0.3 repeating, we'd be saying our density value is much more precise than what we actually measured. Therefore, we need to be able to properly round calculated answers. The first step in doing so is learning how to count significant figures. There's a set of rules that will help us count significant figures. These rules are posted on the course website, so you don't have to write them down as you listen in the video, though you're welcome to if you prefer. You should bookmark or print out the list of rules from the course website, as you'll be needing that for in-class and homework assignments. We'll start with the simplest, most straightforward rule. In a measurement, every non-zero number is a significant figure, meaning digits 1, 2, 3, 4, 5, 6, 7, 8, and 9, when they're in a measurement, are always counted as Sig Figs. This measurement here, 123 centimeters then, has 3 Sig Figs. It's when we start talking about zeros that things get a little hairy. So let's start with 2 rules that tell us when zeros are significant. Zeros are significant when they are between 2 Sig Figs. In other words, say we take a measurement of 103,200.4 milliliters. These zeros here are between 2 other Sig Figs. Therefore, all of those zeros are significant, giving this measurement 7 Sig Figs. 1, 2, 3, 4, 5, 6, 7. Zeros at the end of a number to the right of a decimal point are also Sig Figs. For instance, 9.000 grams. These zeros are to the right of a decimal place at the end of the number. These zeros signify that we actually measured to that many decimal places, and each of those decimal places was a zero value. Therefore, this measurement has 4 Sig Figs. Now let's look at a situation where zeros are not significant. Leftmost zeros in front of non-zero digits are not significant. In this measurement, 0.0071, these zeros are merely placeholders. They put us in the right order of magnitude, but do not affect the precision of our measurement. Therefore, they are not significant, giving this measurement 2 sig figs. 1, 2. To further demonstrate that these zeros are placeholders, consider this. We could get rid of them without changing the measurement. We could, say, convert units and call this 7.1 milliliters. The zeros are gone and our measurement hasn't changed, and it still has 2 sig figs. We could also write it in scientific notation. 7.1 times 10 to the negative third milliliters. Again, we have not changed the value of our measurement, but we've eliminated those zeros. This measurement still has 2 sig figs. These digits here are not considered sig figs when we deal with scientific notation. Finally, zeros at the end of a measurement to the left of an understood decimal are not sig figs. For instance, 300 kilograms. Notice there's no decimal place here. This indicates that those zeros are uncertain. It might be 290 kilograms. It might be 315 kilograms. We don't really know. That means that this measurement has 1 sig fig. An important note, though, if we wanted to indicate that those zeros were measured and were known precisely, we could simply add a decimal point, making all 3 digits significant. There's one final kind of strange case that I want to address really quickly. There are times where we could actually have unlimited sig figs. Take this example. Imagine we are counting Disney princesses. We've got that's Cinderella, that's Ariel, that is Snow White, yes, Snow White. So we have 3 Disney princesses, 1, 2, 3. This counted number of 3 Disney princesses is precise to infinite sig figs. We could have the most precise Disney princessing measuring device known to man that could measure to billions and billions of decimal places. We will never detect a fraction of a Disney princess, unless you're watching some freaky version of Disney. We will always have exactly 3. We could put zeros on the end of that number forever. We will never detect a little bit of Disney princess. So counted numbers have infinite sig figs. Likewise for exactly defined quantities. 60 minutes equals 1 hour. 60 minutes will always equal exactly 1 hour. We can add zeros to the end forever. We'll never have 60 minutes equaling 1.02 hours, or 1 hour equaling 61 minutes. Therefore, each of these cases, counted numbers and exactly defined quantities have infinite sig figs. Let's try putting these rules to use. We'll do one of each of these groups together, then you should pause the video and try some on your own. It's important to have the rules in front of you for now. Eventually you'll need to know the rules without the sheet, but use it as you learn. Take a look at number 1. Here we have 3 non-zero digits, making each of these significant figures, and our 0 is to the right of the decimal at the end of the number, making it significant. Here then we have 4 sig figs. Let's also try a rounding example together. We want to round to 3 sig figs here. In order to do that, we're going to count from the left to our 3rd sig fig. 1, 2, 3. Look to the right, and just like any other form of rounding, if it's 5 or higher, we round up. If it's less than 5, we round down. So this number will round to 317 grams. 1, 2, 3 sig figs. Pause the video here and try these on your own with the rules in front of you. When you come back, I'll reveal the answers. Welcome back. These are the answers you should have gotten. If you got all or most of them correct, great. If not, we'll have plenty more opportunity to practice in class, so don't worry. Now let's move on to the final of our objectives for this video, rounding calculated answers to the proper number of Sig Figs. There are two simple rules for knowing how to round your calculated answers. If you're dealing with addition or subtraction, you're going to round your calculated answer to the same number of decimal places as the measurement with the fewest decimal places. If you're dealing with multiplication and division, you're going to round the answer to the same number of Sig Figs as the measurement with the fewest Sig Figs. Let's try putting these into practice. We'll do two together, then you can pause the video and try some on your own. To begin, we want to calculate a raw, unrounded answer. For the first one, we end up with 8.63 grams. Now, since this is an addition problem, we want to round to the same number of decimal places as the measurement with the fewest decimal places. So counting decimal places, our first measurement has 1, our second has 2, and our third has 1. Therefore, we want to round to 1 decimal place. The first decimal place is a 6. Look to the right. It's less than 5. We get 8.6 grams. Let's try number 2. First, we want to report a calculated unrounded answer. In this case, we get 136.25833 grams per milliliter. Since this is a division problem, we want to round to the same number of Sig Figs as our measurement with the fewest Sig Figs. So let's count Sig Figs. Here we have 1, 2, 3, 4, 5. That zeros between two non-zero numbers, making it significant. Here we have 1, 2, 3. Zeros at the end of the number to the right of the decimal are significant. Zeros at the front of the decimal without a number in front of them are not significant. So we want to round to 3 Sig Figs. Count our third Sig Fig, 1, 2, 3. Look to the right. We round down because it's less than 5, so we get 186 grams per milliliter. Pause the video here and try the last two on your own. When you come back, I'll reveal the answers. This is what you should have gotten. Again, if you got these all right, great. If not, we'll practice in class. That brings us to the end of our Sig Fig video. Let's review our goals. First, we learned to identify which digits in a measurement are significant and which digits are not. And again, those rules are posted on the course website. Then we learned to round to a specified number of Sig Figs. And that was in order to be able to round our calculated answers properly. Addition and subtraction, we go by decimal places. Multiplication and division, we go by Sig Figs.